Now today's topic of discussion is electric dipole and quadrupole moments. Now when a charge current distribution system interacts with an external electromagnetic field, then the interaction energy can be expanded in terms of electric and magnetic multipoles. Now if we assume that the velocity of the constituent particles, for instance here the nucleus, the velocity of the protons and neutrons are much less compared to the velocity of the light, and the applied external field is much less compared to the fields of the parent nucleus, then in that case few lower order multipoles are sufficient to calculate the interaction energy. The interaction energy between the external electromagnetic field and the nucleus is written in terms of this, where this is the interaction energy. Now this is the electrostatic potential, electric dipole moment, magnetic dipole moment, and this is the electric quadrupole tensor. Now this is the interaction energy. Here E and H are the applied electric and magnetic fields. Here E and H are applied electric and magnetic fields. And phi is the electrostatic potential energy. Phi, the quantity phi, is the electrostatic potential energy. Now this subscript 0 means that the quantities are evaluated at the origin. The subscript 0 stands for that the quantity is to be evaluated at the origin. The symbol P is the electric dipole moment and M is the magnetic dipole moment, and Qij is the electric dipole tensor. Now the electric dipole moment for an assembly of charges, the electric dipole moment for an assembly of charges is written as is R rho d tau. D tau is the volume element and rho is the charge density. Now where rho is the charge density, now any system with a definite parity cannot have static electric dipole pole of odd order. That means any system which have a definite parity, they cannot have the static electric pole of odd order. Now any system with a definite parity cannot have static electric pole of odd order Now the question is why? Why the system with definite parity cannot have the electric pole of odd order? This is because the Legendre polynomials of odd order are odd functions of Z, whereas the probability density psi mod square is an even function of the position, because since the Legendre polynomial of odd order are odd functions of Z variable, while psi mod square, the probability density, is an even function. Because in quantum mechanical problem, this in the expression of the dipole moment, this charge density that will be replaced by the probability density. Now, therefore, the whole integrand will be an odd function, so the integral will be 0. So, no contribution comes from the odd order poles. Now, the electric dipole moment is 0 for atoms and molecules in the stationary states. Therefore, the electric dipole moment is 0 in the stationary states. And this is a consequence of the symmetry of the nucleus about the center of mass, or it is a consequence of the definite parity of the nuclear states. However, this symmetry does not need to be spherical. There may be an ellipsoid of revolution. The deviation from spherical symmetry is expressed by the electric quadrupole moments. Now, we have assumed in case of determination of nuclear size that the nucleus is most generally spherical in nature, but there are certain nucleus which are not spherical in nature because they have a large quadrupole moments. and deviation from spherical symmetry is determined by the quadrupole moments. So now we shall calculate the quadrupole moments. In particular, the quadrupole moment is the lowest order of interaction with an external electric field. Now we assume that an electric potential U x y z is applied across the nucleus, and the nucleus having a charge density rho x y z. Nucleus has this charge density rho x y z, and an electric potential is applied in the nucleus. Then the total electrostatic energy resulting from the interaction between the U and the charge density can be calculated. Now when this charge density will be placed in this external potential, then due to interaction, so we get the interaction energy, and that interaction energy can be obtained by expanding this function U in a Taylor series about the origin. Now, therefore, the electrostatic interaction between the U and rho can be calculated by expanding U in a Taylor series. Now, therefore, the interaction energy can be expressed as the interaction energy between U x y z and this rho can be expressed as E U x y z rho theta. Theta is the volume element. Now if we expand this U x y z in a Taylor series about the origin. Now the expanding U x y z in a Taylor series about the origin. Then one gets that E equal to U of 0 rho d tau plus del U del x at 0 x rho d tau plus del U del y at 0 y d tau plus del U del z half del 2 u del x2 x square rho d tau plus similarly y term plus half del 2 u del y2 0 y square rho d tau plus half del 2u del z to 0 z square rho d tau, and the cross terms del 2 u del x del y at 0 x y rho d tau. Similar other two terms plus you get del 2 u del y del z at 0 y z rho d tau plus del 2 u del z del x x z rho d tau plus higher order terms that are neglected. Now the last 6 terms here 1, 2, 3, 4, 5, 6, last 6 terms in this expression are quadruple terms. Now not all these terms are say linearly independent, and for an ellipsoidal rotation a single quadruple moment sufficient to describe the interaction, because here all these 6 terms they are not linearly independent, and for an ellipsoidal evolution, if we consider the nucleus is an ellipsoid of revolution, not properly spherical, then these last 6 terms, out of this, one term is sufficient to calculate the electric quadruple moments. Now because of symmetry, the 3 terms, the cross terms, because of symmetry, the 3 integrals involving the cross product x, y, y, z, and because of symmetry, the last 3 terms involving the cross products vanish. Their contribution to the quadruple moment is 0. So the last 6 terms, contribution from these last 6 terms is 0. Now when z axis is considered as the symmetry axis, suppose it has this type of distribution, or either it may be this type of distribution, ellipsoid of revolution. So this is your z axis, symmetry axis. So as z axis is the symmetry axis, so integration over the x square, in this plane is the xy axis, so the integration over the x square or integration of the y square will be the same. That will give you the same results. So therefore, if we calculate any one of them, either one x square or y square, then we get the results of the other. Now therefore, as z axis is the symmetry axis, as z axis is the symmetry axis, the integral over y square gives the same result as the integral over x square. Therefore, the quadrupole interaction energy therefore the quadrupole interaction energy say delta E2, it is half del 2U del F2 z square rho beta plus the other two terms plus half del 2U del x2 plus del 2U del y2 at 0 integrate over x square plus y square by 2 rho beta. Now we know that the Laplace equation, the one from Laplace equation, what is Laplace equation? That is del square phi equal to 0 or del square u equal to 0. That is del square u equal to 0. That means it is del 2 u del x2 plus del 2 u del y2 plus del 2z del u2, that is minus del 2 u del z2 and know that r square is equal to x square plus y square plus z square. Cartesian coordinate system, r vector is x square plus y square plus z square. Now if we substitute all these values in the expression for delta E2, substitute all these values in the expression for delta E2, then what we get? Substituting all these values in the expression for delta E2, then what we get? Delta E2, that is 1/4 del 2u del z2 and z is equal to 0. Figure of 3z square minus r square rho beta. In case of x square by y square, we put from this relation r square minus z square. And that is equal to written as delta E2 is written as EQ by 4 del 2u del z2 at 0. Well, Q is the quadrupole moment and it is written in terms of this integral 1 by e times, because e was not here, it is written here extra. Now therefore the quadrupole moment Q or the quantity quadrupole moment Q, where the Q quadrupole moment, that is 1 by e z square minus r square rho. Now, now if the charge distribution is spherically symmetric, perfectly spherical, then what will happen? For a sphere, x, y, z are equal, so this r square will be equal to 3z square. All x, y, z are equal, so in that case you get q is equal to 0. So if a nucleus is spherical in nature, that means its charge has the spherical symmetry, charge distribution has the spherical symmetry, then its quadrupole moment will be equal to 0. Therefore, for a spherically symmetric charge distribution, 0, because in that case r square equal to 3z square or 3x square or 3y square. Now, if the charge distribution is not spherical, instead, if the charge distribution is traced along the z-axis, suppose this is your z-axis, which is called the Coulomb distribution, instead of sphere, if it is an ellipsoid of revolution as traced along the z-axis, or say it is like this, oblate distribution or oblate. For Coulomb distribution, so z is larger than x and y. So in that case, a 3z square will be larger than r square, and this quantity will be positive. So for Coulomb distribution, we get positive quadrupole moment. That means if a nucleus, for a nucleus, if your calculated quadrupole moment comes positive, then you can say it is a Coulomb type of distribution. And if it is oblate, then in that case 3z square will be less than r square, and in that case the q will be negative. So for negative quadrupole moment, it is oblate distribution. Now, when we find any observable in quantum mechanical problem, then we always take its projection along the symmetry axis. Now, if we consider here the j-axis as the symmetry axis, that is j means the spin of the nucleus. If j-axis or direction of j is considered as symmetry axis, then the projection of this j on the z-axis, that is the value of mj, that is the projection of j on the z-axis, that is mj. Now then in that case what we get, that is cos theta, the angle between then we get that j cos theta, that is equal to mj, that is a numerical value. We know that j square is equal to j into j plus 1. Then what will be the value of j? That is square root of j into j plus 1 into cos theta, and that is mj, its value, maximum value of it is j. Now therefore in that case the cos theta, the angle, you get j divided by square root of j to j plus 1, that is square root of j divided by j plus. Now this relation actually not valid for j is equal to 0. This is not true for j is equal to 0, because for j is equal to 0 we have no projection at all. So this is not, say, for j is equal to 0. This is not for j is equal to 0. Now therefore, if we calculate the quadrupole moment observed along the symmetry axis qj, now you calculate say q, that is 1 by e 3 z square minus r square rho beta. What is z? Here z is equal to, that is r cos theta. Therefore we get, say r is equal to z by cos theta. Now cos theta here is this one, so you get z. So r square equal to, r square is here, so your q will be equal to 1 by e 3 z square minus r square. R square is z square, z plus 1 by z rho d. And that is 1 by e z square into 2z minus 1 rho theta. Now look at this equation. When j is equal to half, then what will happen? From this equation, when j is equal to, say, half, if j is equal to half, then also you get the q is equal to 0. That means when j is equal to 0 or half, you get the quadrupole moment will be equal to 0. So that means a nucleus with spin half, j is equal to half and j is equal to 0, they have the 0 quadrupole moment. But this does not mean that the nuclei with j is equal to half and j is equal to 0 is completely spherical in nature. But what does it mean? That they are symmetry does not show in the static electric quadrupole moment. This does not imply that nuclei with j is equal to 0 and half are spherical. But it simply means that their asymmetry does not show up. In static electric quadrupole moments. Now, next we discuss the parity and symmetry. As we know that the parity is a conserved quantity and symmetry is a conserved quantity in atomic and subatomic region, that is in quantum mechanical problems. But it has no counterpart in classical mechanics. In classical mechanics, the parity is not a conserved quantity. Now, what is parity? That means if a wave function, parity and symmetry, if a wave function does not change its sign under reflection, that is x goes to minus x, y goes to minus y, or z goes to minus z. If it does not change sign, then it has a positive parity. And if the wave function changes sign under reflection, then it has the negative parity. Now, the wave function may be considered is not single particle wave function, maybe for many particle system, the total wave function may be written in terms of the product of all single particle wave function or the sum of the products of such wave functions. So, in that case, the total parity of that wave function will be the product of the parities of individual particles. Now, therefore, if a wave function changes sign under reflection, then it has positive parity. And if the function does not change sign under reflection, then it has positive parity, and if it does, and if it changes sign, then it has a negative parity. That is, if it writes psi x y z is equal to psi of minus x minus y minus z, then positive parity, and psi of x y z is equal to minus psi of minus x minus y and minus z, then it has negative parity. Now, as the probability density of the wave function, that is psi mod square, is a positive definite quantity, therefore always the mass and the charge densities are always positive. Now, the another significant quantity is the symmetry of the wave function. Now, if we consider say two identical particles, suppose both are protons or both are neutrons or both are electrons, so you cannot distinguish one from the other. Suppose two identical particles are there, non-interacting particle, and they are moving in the same potential field. Let two non-interacting, that means they are completely isolated, two non-interacting identical moving in the same potential field, then the total wave function say psi, say n k, one is in the nth state and one is k state, that is psi n 1 and psi k 2. This 1 and 2 means the particle number 1 and particle number 2. We designate that the particle number 1 is at the nth state and particle number 2 in the kth state. Okay. So this is the total wave function because they are the non-interacting. So the product of these two is the total wave function of the system. But the wave function psi n written in this fashion, this is not acceptable for two identical particles, because if the particles are identical, then we cannot designate it as 1 and 2. Suppose there are two particles, say two protons are there, or say two neutrons are there, then whether it is at nth state or whether it is at k state, suppose say it is at psi n, it is at psi k. So you cannot say definitely that this is at the kth state or this is at the nth state, or whether it is at the nth state or it is at the k, because they are identical. You cannot distinguish between them. So in that case, you cannot say label them as particle 1 and particle 2, and in that case this form of wave function does not hold good. This is not an acceptable solution. So in such a case, what will be the actual wave function? So to avoid this confusion, one may write the wave function in this fashion, either symmetric or antisymmetric. Then in that case, the psi s and the symmetric wave function, s stands for symmetry, that is 1 by root 2 psi n 1 psi k 2 plus psi n 2 psi k 1. Or if the wave function is antisymmetric with respect to the exchange of the particles, then it is written as psi n 1 psi k 2 minus psi n 2 psi k 1. S stands for the symmetric wave function, and this is antisymmetric. A stands for the subscript antisymmetric. With respect to the exchange of their position. Now if the particles, here we consider the protons and neutrons, we know these are all spin-up particles and they are fermions, and their wave function with respect to the interchange of the position, their wave function is always antisymmetric. And if the particles are bosons, that means the integral spin particles, then their wave function is always symmetric with respect to the exchange of these particles. So we know that for the fermions, there is a strong repulsion between them, which is a consequence of the Pauli's exclusion principle. We know that no two fermions can have the same four sets of quantum number. Okay. Now that originates from the Pauli's exclusion principle, that is the wave function must be antisymmetric. There is a strong repulsion. Whenever they exchange with their position, their function will be antisymmetric. So this is a consequence of the Pauli's exclusion principle, or sometimes the repulsion, strong repulsion between the fermions. Now in the next class we shall discuss the semi-empirical binding energy formula.